Okay, good evening, everyone. So I'm Guozhi from Humboldt University of Berlin. I'm very happy to have the opportunity to present some of our recent works in this very interesting workshop. First of all, let me thank the organizers for the organization of the workshop, and in particular for giving me the opportunity to present the recording of my talk instead of a talk live. Therefore, I might not be able to answer your questions after my talk. However, I will leave my email address so that if you are interested in my talk, please feel free to drop me emails if you have questions. I'm very happy to discuss with you. Okay, so this is a joint work with Michael Henteminer and Kostas Papafitoros. So Michael is a professor at Humboldt University, and he's also the director of the Weierstrass Institute, and Kostas is a postdoc at Weierstrass Institute. So in this project, we study a general optimization framework subject to some learning-informed differential equation constraints. So in this talk, I first introduce you this general framework, and subsequently I will give two concrete examples which also motivate our study. Okay, so the optimization problem we're going to study is actually summarized in this green box on the right-hand side. So here are the objectives. You see, it consists of two components. The first one is a kind of data fitting term, which are quite standard in inverse problems or in imaging problems. And the second one is again quite standard, so it's kind of Tikhonov regularization. So the parameter y and u are the unknowns, and g are the measurements, and a is a linear operator. So the y and u are connected through an operator equation. So y equals pi n u. So the pi n is a learning informed operator, which corresponding to the title. And u itself might have some additional constraints, since u is some physical parameters. So usually it has some uniform bounds on the quantity or on the magnitude. And this type of learning informed operator is intended to approximate some underlying physics models, which we call it y equals pi u. However, this pi u might not be known to us, or only partially known. So this is because it is characterized some physics process, and for this physics process, you only have some observation where you give some input, you observe these output pairs. So the input and output pairs are known. So the idea is to learn this underlying physical operator pi using some learning informed techniques, for instance, artificial neural networks. And we have some application in mind. So here there is a phase separation, and another one is a quantitative magnetic resonance imaging, where both have this type of properties. I will come to the examples later on. So before I introduce the general framework in more detail, since I already mentioned there is a learning-informed operator involved, so I try to somehow review the current state of artificial neural networks. So from the functional or function approximation point of view, since I'm still quite new to this field, so this summarization here might be quite biased. Okay, so I consider a map to be classified in 4 categories. In the first one, we can consider a map between finite dimensional space. And this has been well understood in the literature for artificial neural networks. So in particular, if the domain is bounded, and we have this universal approximation theory, which says this f can, a continuous function f basically, can be well approximated by artificial neural networks. And there are applications, for instance, the standard regression in statistics. So the second category, so F then is a map between infinite dimensional space and finite dimensional space. So for instance, you can think of this image classification, where the image can be considered an object in some infinite dimensional space if the image is a continuous function, for instance. And you try to classify the images, for instance, try to classify dog, cats. Therefore, the mapping is to some real numbers. A very so currently a very well developed tool for this is like convolutional neural networks, which can do tremendously good work for classify images in particular. However, the theoretical part for instance, universal approximation type property are still largely open for this type of tasks, in particular for artificial neural networks. And the third class I would like to mention, which is also currently a hot topic, is to use neural networks as ansatz for the solution of partial differential equations. In this case, F will be a map from some bounded domain in Euclidean space to infinite dimensional space. So F is an object in some function space, where the function space as a solution space of the PDE. And there are many numeric methods proposed. However, I would consider which is open is the theoretical understanding, where, for instance, the convergence, right, or even the universal approximation type theorem are still cannot be directly applied in many of the cases for PDE solutions. And for the fourth category, as I already mentioned in the previous slide, is kind of operator learning. So here is a map between infinite dimension space. So this is even less concerned in comparison to the problems in the first 3 categories. So the main difficulty is because of the lack of compactness, which makes the theoretical understanding and also the algorithm development are fundamentally difficult. Okay, so let's come back to our general optimization problem. So here, I consider the operator equation to be implicitly characterized by some partial differential equations or system of differential equations. So assume that this equation is well posed. In many cases, we have the prior understanding of the PDEs. So given an input U here, you should be able to find a unique Y. And in this sense, we call this map is well posed. And we can come up with this solution map of this PDE or ODE. Okay. Based on that, we are interested in find some neural network approximation of this solution operator pi. However, as I already mentioned, this task is fundamentally difficult. So it might be for a specific problem, we need to find a specific method also. So in general, I guess there should be no universal method for the operator learning problems. The fundamental questions we can ask here, in particular from the theoretical point of view, I can summarize the three problems here. And the first one is the well-posedness of the learning-informed operators or the learning-informed PDEs. So how about the existence, uniqueness, and stability of the solution? After this is well established, and we can ask whether there exists a universal approximation property of this learning-informed operator pi m to the original solution map pi. And further, we can ask how about the approximation of the optimizers of the two optimization problems. So one is the learning-informed optimization problem, and the other is the original optimization problem. Are the optimizers close to each other? And what about error bounds between them? So in this project, we can actually have answered these three questions to some extent. Of course, based on some assumptions. And because of time constraint, I will not present the details of the results. Instead, I gave you two concrete examples. So the first one I'd like to mention is optimal control of some semi-linear elliptic PDEs. So here you remember we have this E, Y, and U equals 0, which are now replaced by this concrete PDE here, where the feature is that it characterizes some physics process, since the diffusion usually can be observed, and then we can put the rest as some nonlinear map, which is a kind of a modeling process. And what we are interested in is actually the solution map, right? So we try to give a U, we try to find the Y. So the goal is to learn the solution map for this type of a PDE. And how to learn this? And we already found that this task actually is not so trivial. So the idea for us is that instead of learning the solution map itself, we try to focus on the nonlinear path. So we try to replace this F by some learning-informed operators or by some neural network operators. Okay? So the idea is that we use some neural network function to represent or to approximate this nonlinear map F through this relationship. Okay, so this is a non-trivial task. And I will not explain in detail here, but if you are interested, please feel free to drop me email. We can discuss in details. So after we have learned this, we insert this n into the PDE, and we can, of course, establish the well-posedness and also the differentiability of the solution maps and so on. Then after that has been established, we can then prove some universal approximation property for the solution map of the learning informed PDE and the original PDE. So given F satisfies some assumptions, and actually using the universal approximation theorem for the map in finite dimensional space for bounded domains, we can actually have this result immediately. And based on this approximation, we are able to prove that the solution operators can also satisfy some universal approximation. So this C is kind of independent of this epsilon, but it depends on the bounds of the CAD here. Okay, and even further, we can prove the directional derivative of these solution operators, the universal approximation property. So basically, the P is some directional derivative of this pi m up to some direction, and this P epsilon is some directional derivative of this pi n up to the same direction, of course. And we can prove this type of estimates, given this can be guaranteed again by the universal approximation theorem in finite dimensional space. Okay, so this is what we can prove for this type of problems. And instead of going too much details to the numerical algorithms, I just here gave you some visual comparison of the learning informed solutions of the learning informed optimization problem, and this is the original sense we cook up some examples. So here is the uncanny equation. We set it as a benchmark example, and we use the learning informed models to approximate, which shows that the error somehow matched to what we can show in our theorem. Okay, and in the second example, we consider this quantitative magnetic resonance imaging. So here the model is called Guozhi equation. So this is the UYU equals 0. And the interesting quantity is this rho, which is the density, the proton density, and T1 and T2 are coordinate times. So we are interested in reconstructing these three parameters, which I summarize as U here. Okay, so the F is like the Fourier transform, and the P is a subsampling operator. So we try to see how learning informed operator can help for this task. So you can say that this PD, this OD actually, so because Guozhi equation has no spatial derivative involved, so it's OD, can be significantly simplified if you introduce this learning informed operator. So you can directly learn this map from U to Y if you have some data pairs available. And this is then, based on that, we can again show the universal approximation property of the learning informed operators. So this turns out to be quite standard in comparison to the one for PD. Okay, and again, I can show you some numeric results without going into too much details. In case you are interested in the algorithms, please also refer to our paper. Okay, so the results just indicate that the learning-informed operator can produce a satisfactory result for the quantitative magnetic resonance imaging. Of course, this is based on some synthetic data. In order to deal with the kinetic data, there is still a big gap. We have to find some way to fill. Okay, now let me summarize the talk. What we offer here is a general optimization framework where we consider some constraints from learning-informed differential equations. We have implemented both the analysis and also numerical algorithms. And we have introduced some way to learn solution maps for particular PDEs and ODEs. And we also show that there exists a universal approximation property for this type of approximations. What is ongoing that in the existing work, we have only considered smooth activation functions, therefore smooth operators, but in reality, there might be non-smooth operators, and in particular, in learning, people using non-smooth activation functions or not. And therefore, when you introduce this non-smooth into the optimization, this makes the story are rather complicated than the smooth optimization problems. And therefore, there is huge efforts needed for the theoretical analysis and also for the numerical algorithms. And there are more going on for learning the physical operators and also the interplay between operator learning and the optimization problems. In case you are interested in our results, or you're curious about our results, please feel free to refer to this paper. I think you can find in archive or in this VS server. And I'm also open to questions. If you want to discuss, please feel free to drop me emails. And that's all what I want to talk, and thank you for your attention.